If you follow any space activities recently, you know that going back to the moon, landing safely, and establishing a colony and a lunar economy is something that is top of mind of many companies and also nations. And this is a difficult thing to actually achieve. And I was fortunate enough to recently talk with Astroport's CEO, Sam Ximenes, here in San Antonio about the plans that they have to make this a reality. And we had a chance to talk with him at length about making some bricks for a landing pad and also the process that goes into that by touring their laboratories. And I did put out some videos on that very recently. And there was a lot of interest in what was being discussed. So fortunately, today, Sam Ximenes was part of a discussion group with the Lunar Launch and Landing Facilities Workshop. And he talked a lot more about their plans, how they envision this process working, some of the challenges, and also just what are their basic plans for the future to run a port, a gateway on the surface. So I thought I would give you a chance to listen to Sam's discussions and hear from his own words about this process. So let's get into the video and let's hear what Sam had to say. And I hope that you find this informative.
Hand it over to Sam Ximenes. He's a space architect with over 30 years of experience in the aerospace industry with NASA and DoD and international space programs. He's currently the CEO of Exploration Architecture Corp, or XARC, a space architecture consulting firm he founded in 2007. The firm specializes in commercial spaceport development and design and space system development for space exploration initiatives for planetary service systems for habitation and human settlement. His latest venture is Astroport Space Technologies, which I'm sure he'll be telling us more about. Sam?
Thank you, Jibu. I really like Paul and Rob. He's always got the big picture view of things. I'm going to also present a vision here, but bring it down to the vision that we have for how spaceport enables the economy of the lunar base and lunar cislunar economy. So, and we began that with what we call fixed base operator services. Just like in any airport, general aviation airport, there is a fixed base operator that takes care of the coming and goings of the landing and the takeoffs of the aircraft and the fuel refueling, their maintenance, their hangars, and it's the basic general operations of the airport. So we have the same sort of situation with the development of the spaceport. Let me just go back into the goal of Astroport here. Astroport is a young company that we've been around since 2004. 2020. But we started looking at the idea of the need for the landing pads because we were looking at before that the spaceports on Earth. So,
hey, Sam, sorry, the audio is a little choppy. So I don't know, maybe if you want to cut the video, or get closer to the mic.
Let me see if I get the video up here. Sorry about that. Better?
I think that's a little better. Thank you.
Okay. All right. So our goal here is to not just build the spaceport. We want to be in the business of the operations of the two. We began all this by understanding the materials that we're going to work with, and the working of the materials, of course, is the regolith, and then how you use that regolith as the natural resource for solidifying it or making it as a building material. And then what goes with that, how do you actually use the construction process of the material to plant it into whether it's a habitat or landing pad. Then finally the operations that come into place. And this community everybody knows about regolith and how it can be used, the resources of the regolith could be extracted gases and then solidified into building materials. This is the kind of things we're doing at Astroport. There are a lot of approaches to the building of a landing pad. Ours is a solidification of the regolith, for turning regolith into bricks to make a pavement. and understand how that is used in terms of melding the bricks together into forms so we don't have to use grouts. Then how do you put that into a robotic platform to put them on the ground to make the actual pavement? But now let's talk about the construction part of it. We're also working on the end-to-end system piece of this. How do you actually go about the beginnings of the site preparation? We just came out of from last year a study we did for NASA for the bulk regolith movement and excavation of the regolith, so that we can site prep the location and level the site. And looking at everything from the concept of operations to the actual architecture that you would use at the site, and then the robotic platforms that are part of that, all the assets that you have to bring with you, and then the regular distribution system to put in place. In our case, we need to have for the feedstock to make the bricks, and then then also the foundation and the structural elements and the geotechnics to go into the actual pad design. So that's kind of a building blocks of it. Now, in terms of the vision piece of where are we going? How do we get there? Our goal here is to, this is a picture of a location close to a lava tube. It's, the end of the century, hopefully, we've got this sort of a technology that's generated where we can actually have this thriving economy going on. The pad begins as the gateway to enabling the community, for crucial access for the cargo. The logistics supply chain is going to have to happen for the coming and goings of the economy that's going to be developed there. You have shared resources happening. You have spaceflight operators being able to do their ISRU functions or whatever the mining they're going to be doing. So it becomes a catalyst for essentially a lunar economy. But it begins, here's a bigger picture of it. Again, I know we're going to the poles. We haven't really found latitudes of the South Pole yet to any extent. This is probably more of a Mars Norwegian location, but the same general principles will apply as you develop the infrastructure. You'll have as much infrastructure on the surface as you will on the ground if you're already going to be using latitudes for development. You can see here that they're doing a lot of things. They're doing mining. They're doing extraction of the regolith to produce the rocket fuel and the oxygen they'll need to have. In the background's the spaceport. Now, to begin that, though, you're going to have to start somewhere with the beginning. And this is the very, very first piece of this. This is probably the next decade. We'll have the first pads built up. This decade, it's going to be more technology testing of the technologies. We have, in our case, we want to be able to get up there and show them we can actually make a brick on the moon. But eventually we'll have, I think by mid-decade next year, the first pads being developed for the coming goings of space pad. Then from there, we look into the ability to start the first economics of it. In our case, we will take the regolith that we've already excavated and reuse those tailings that come out of what we didn't use for making the bricks as stockpiling for materials for other uses. For example, ISRU uses like oxygen extraction and metals extraction and it's basic processes that you could use for making the regolith a commodity. We will deliver our goal is to deliver the regolith process to these operators. They don't want to be in the business of doing excavation for the processes. So we'll already be there with our excavation materials and assets that we can just deliver to these different mining locations for what they need to have for their processes as well. Then we get into the part of the mid stage where we're doing the recycling. Things that come on back to the surface. We want everything you bring to the lunar surface is going to be usable and reusable for repurposed. We get into the depot facility where we take, for example, spacecraft that are descent stages that are left behind, chop them up and bring them into the chop shop and reuse all the metals and everything we can out of there. In this case, we're working with the ability to make the additional feedstock out of the lumen that's brought up there and turn it into additional stock for the building materials as well. You can see the beginnings of the layout of the base itself, where you have again the surface mining going on, the oxygen storage facilities, and the top image there on top of the landing zone itself, and the beginnings of the construction of this again in the case of the lava pits that are there. Now we get to the final stage again, back to the end of the decade, like I said earlier, end of the century. Hopefully, we have a thriving economy where we've been able to cover that lunar pole and dome and get out of the spacesuits, get out of the cans basically, and have more room to move around. This is this is the construction aspect of how do we do all this? And this is horrendous types of technologies that need to be developed and yet to be developed. And we'll have new materials and new processes that we'll be able to employ. Of course, in the next coming decades before we get there. So that's the vision we have at Astroport, where we're going. We begin with the landing pad. Thank you very much. The end product of the pad, but the actual site preparation. How do you get to a point where you've got a prepared site and to lay down the foundation and level it, especially when we go to the lunar surface on the South Pole. It's very hard to find flat sites as opposed to on the mire areas. So we ended up doing I mentioned this earlier in the morning, the study we did that did a comprehensive look into how do you actually go from an end-to-end system approach for the construction of the landing site. And this is in particular to our own technique of the brick making process that we have. One of the first things we wanted to do was just to benchmark an actual site that we would identify and map it out, understand the topology and the terrain there. We chose through a criteria scoring process the Gerlache Ridge, and there's been a number of other efforts to choose identify sites, and a lot of them seem to land on the Gerlache Ridge. So I think, and they've all come at it from different angles in terms of their criteria. Lighting, for example, and topology, slope angles, flatness, and openness. Ability to have enough room to have a large enough activity zone for construction. So that seems to be the consensus evolving around this location. So using this location, we had to pin down into where exactly in there is the flattest spot we could find, and we started did some modeling, and there's a area there about 11 kilometers from the edge of the rim of the Circling crater, and then trying to see where we could actually not only have the flattest site, but what kind of geographic features are around there that we could take to our advantage in terms of the overall layout of the site for future growth. For example, habitation zone. This did not go into habitation. How do you build in the habitable zone, but what we wanted to do was find an area where we were higher for the eventual location of the habitation zone, and the elevation would be lower for the actual construction site where the landing pads would be developed over here. So you can see the elevation that's been developed here, and I think there's another picture here of some of that elevation. So and then within that 2 kilometer area that we identified. Where within that again, where's the flatness? We had 3 options we looked at, and trying to again find see where we had the least amount of energy requirements for excavation and cut and fill. And you can start seeing here within that 2 kilometer area. Then we took going down to a 330 meter square area of the pad site itself. The pad itself is 100 meters, but we had to take into account the again flatness and leveling for other activities. And you can see, we started identifying that, the amount of leveling which is going to be required for cut and fill operations. You can see on in the corner there, the profiles of that, just that one 330-meter square area. From there, we started try to do understand what is the amount of cut and fill that we needed to do, and do we cut down to make a level surface, or do we fill to make a level surface? And what's that trade in terms of the amount of the quantity of regolith that you're going to be moving? And we're talking tons of regolith. These 3 areas, just the movement of some meters will change the calculation in terms of how much dirt you're going to be moving around. One of the things that we chose number B, or selection B here, even though it has more cut to it than less cut to it than the other ones. One of the reasons is that we also, in our process, this is particular to our own process, where we need to have source feedstock material for making the bricks. In addition to that, we have a bagging process where we have to where we're making the berms out of a facing of what we call Regol packs, or essentially they're the lunar regolith filled bags, sandbags, if you will. And so having the idea of having the need for this extra material while we're doing the excavation, that was the reason we went down to a cut approach. So going into the architecture, what's the actual shape of that? There's all kinds of shapes you could come up with in terms of the outline of the pad and the optimization of it. One of the more relevant requirements is the egress. We believe it's going to be a need for dual egress of the pad when you start surrounding them with berms. And so we took a look at those, and then settled on option B there, this configuration we call an I configuration. And again, moving that configuration, any one of these configurations within that 180 meter diameter or 150 meter diameter gives you different quantities of dirt to be moved around. Again, whether it's a cut, in this case we're talking about a fill configuration or a cut configuration, which is the one we landed on, again, where we cut down into down to, not to the bedrock, but we were going down about 3 to 4 meters in depth to get there. And then we were building ramps to come in and out of it. So doing that, then we, this again, I mentioned this early in the morning, we're doing the brick construction, where we're actually making these bricks in place with this process we have for binding the bricks, infusing them as they're being printed out. And we have to also deal with the robotics to go into that. How do we place it with the robot? So those are all particular to our own process. So it might be a different configuration or a different process in terms of the conops, if you have it like another way of doing your construction piece of it. And then with that comes the regolith distribution system. When we do the excavation and moving all this dirt around, we need to be able to sort it out and fill it, sort it out and process it so that we get the right granularity of the feedstock we need for the brick making. And part of this involves the way we haul it back and forth, and we deliver it to from the excavator and the haulers delivered to the silo system we have. The silo system is one of the technologies we're developing that does a sorted and sieving of it, of the grains into different elements. And then deliver that to what we call our Lunatron brick box as well. So that's an important part of it, because I mentioned early in this morning session that we're at the end of this, we're going to end up with the materials yard, and the materials yard is going to be, we're going to have piles of stockpiles of already processed regolith that can be used, again, part of the economy, where it becomes a commodity for us for resale. That's what this is the example of that here, where we actually are delivering these regolith canisters to customers. I'll talk about that this morning. I'm not going to go into the geotechnics in terms of the design of the pad itself. This is more the configuration we're looking at, where we have a cut down and a leveled surface, and then we're facing the, when we do the cut, we make we're already making the berm, so and then we face it with the bags as well. So that's another part of where it was that decision to go down into the cut configuration. So when we do the excavation, we're going to need to do it's going to be like a swarm of robots that we're looking at in terms of how that works and in the energy requirements that were involved in all that, and of course all the communications and positioning that self-position that needs to be done. There's all kinds of other aspects that are involved. This just shows the profile of that cut of regolith that's moved out, almost 26,000 square cubic meters of dirt being moved out. And you can see the berms being built out, being formed by cutting down into the surface. And then from there, what's the layout of the site itself? How do you do what is that conops in terms of the way you laid out the site and where you have your activity zones? This is showing the initial landing site up here in the top corner where you actually land, and then this is the staging area where you bring all these assets, all your construction assets, your tools and your robots, and your power system and your base station and charging station, and then you have to move away to in this conops. We're moving away for the eventual takeoff after it's unloaded. We believe that the Starship's going to be a valuable asset. It's not going to stick around for the duration of the construction. They're going to want to reuse it for other missions. So it's going to be there for just enough to unload and then leave. So we have to have move everything away from that takeoff of that Starship, and set up a equipment storage area to protect those assets during that period of time. We're also moving, locating the power systems and base stations. These numbers here represent meters, 420 meters of distance from the landing site to here's down here in the bottom corner is the actual pad location itself. This green line, if you recall the other image, three-dimensional image, where this leads up to the hill, to where that habitation zone was at. But then we have your borrow pit or fill pit as well, your sorting station. Again, I mentioned equipment storage. There's a charging station. So these are all the different. These are important to understand the distances between the traverses between these different locations, because that's your energy requirements you're going to have to deal with in terms of your power consumption, and with all these robots moving around. So those are important. We've been doing those kind of calculations to understand what is the total energy power requirements for power and energy to deliver this particular conops. And again,
Sam,
it's just a benchmark.
you have 1 more minute.
I'm sorry, 5 minutes. Okay.
Oh no, 1 minute.
1 minute. Okay. Anyway, so this is more of the conops. You got your site planning set up, your feedstock conops that goes into that. The bricks, the thickness of the bricks is important in terms of the amount of feedstock you need to deliver. The excavation and sorting conops, the communications conops. Does that get in play, and how do you use that? What we're using is the ESA Moonlight system for our communications. The system architecture in terms of the asset that we have, your haulers, your mobility platforms, your compactors, your shovels, your cable layers, and all these things that are, how is this whole complement of equipment brought up in one mission? Is it brought up in one mission or not? We're not so sure. I think it's going to be more than one mission, even at 100 tons of cargo. And then here's the quantifications where we're trying to figure out in terms of the energy requirements for the labor and energy that's required for the robots as well. I think that's it. So we end up with this kind of a configuration with the pad, and then these are just pretty pictures of that same process where you deliver the assets, you set up your power system, your comm system, shelter, your cable laying, your excavation operations. More pretty pictures here, and then I think that's probably all there is. Oh, I want to leave you with this message. I always like to leave at least. I like this picture. Everything time I present this, it's going to be a pretty big task moving all this dirt around. If you see it in the top corner here, this little red arrow, down the little dot below that red arrow is a 95th percentile male. compared against the bulk regolith quantity of movement that 26,000 cubic meters of dirt. So this is a human huge task in terms of what we have to move around, and we're going to be doing that with swarms of robot. Well, we need to really understand the implication of those energy requirements. It's going to take a lot. Okay, with that, that's it. Thank you.